Welcome to the Deep Dive. We're diving deep into the math that makes data science tick today, and I know you're going to love this. You've sent over some really cool bits from 15 math concepts every data scientist should know, so let's crack those open.
Great choice, by the way.
Right? We're aiming for that cheat sheet vibe, but explained in a way that won't make your head spin.
Absolutely. The book nails it. It shows how the math is the real deal, not just theory.
It's the engine. So we've got probability, matrices, time series analysis, even Bayesian modeling, which sounds kind of scary, but I think we can handle it, right?
Oh, definitely.
I'm really curious about that part on probability in e-commerce and how matrices can reshape data. There's even something called singular value decomposition. Does that ring a bell?
Absolutely super relevant for e-commerce, that one. But hold on, before we get too fancy, we got to start with something basic to data science. Randomness.
Okay, randomness.
Yeah.
Sounds simple enough,
Yeah.
but I bet there's more to it than meets the eye.
You got it. The book uses this cool example of measuring pressure with a barometer. You take a bunch of readings, same barometer, but you'll always get these tiny differences. It's not just the tool, it's built into the measurement itself, that unpredictability.
So even with perfect tools, the data has a fuzziness to it.
Yep. Like in e-commerce, customer behavior seems random on the surface, but there are patterns hidden in there.
So it's not total chaos.
Nope. That's where those probability distributions come in. They help us make sense of those fuzzy situations and figure out the odds of different things happening.
So like the odds of a customer adding a certain product to their cart.
Exactly. Imagine rolling a 10-sided die. Each side's got an equal chance, and we can map out all those probabilities. That's your probability distribution. A key thing here is the mean, kind of like the average outcome you'd expect if you rolled a ton of times.
So with that 10-sided die, the mean would be 5.5. Right. Because things should kind of balance out in the middle over many, many rolls.
Exactly. But there's more to it than just the mean. We've got standard deviation and skewness, too, which tell us how spread out and what shape the distribution has. Imagine comparing, say, sales of a super popular product versus a really niche one.
Oh, interesting. The popular one would probably have more sales at the higher end.
Yep, that's skewness in action.
I'm starting to see how the shape of these distributions would be gold in e-commerce. You could predict demand going up and down, or even tailor your marketing.
Absolutely. And those are examples of what we call discrete distributions. But what about things like how much a customer spends or how long they stay on your website?
Those aren't set categories. They can be anything within a range.
Exactly. Continuous distributions like the Gaussian distribution.
The bell curve, that's the famous one, right?
You got it. It's everywhere in nature. And for e-commerce, it might model things like customer ratings or how long deliveries take. Then you've got the binomial distribution, which comes in handy when someone's making multiple purchases.
So if we're analyzing how much people buy during a sale, that's binomial.
You got it. Super useful for inventory and sales forecasting. And that brings us to sampling.
Oh, right, sampling.
The data we get in e-commerce, it's like a snapshot from these bigger probability distributions. Knowing how to create these samples is super important for things like simulations and hypothesis testing.
So we can use these theoretical distributions to make fake data that acts like real customers. That's pretty cool.
Precisely. And there are tricks for doing this, like using what's called the cumulative distribution function, or CDF. Think of it as the recipe book for creating data that follows specific patterns.
Okay, that makes sense. And once we have this data real or simulated, how do we actually make sense of it?
Statistical estimators. They're like our tools for making educated guesses about a huge group of customers, even if we can't look at every single one.
Like if you wanted to know the average order value, but you can't possibly go through every transaction.
Exactly. You'd use a sample of data and an estimator, like the sample mean, to get a good estimate.
And the more data we have, the more accurate our guess is, right?
Exactly. It's like trying to figure out what customers like based on a handful of reviews versus thousands. Crucial for stuff like A/B testing in e-commerce.
Right. You want to be sure that a change to your website actually makes things better, not just random chance.
Exactly. Understanding estimators helps us figure out how much data we need to make good decisions. It's about being smart and efficient.
Makes sense. So it's not just about gathering tons of data, but using it wisely.
Right on. Now let's talk about matrices. They might seem a bit abstract at first, but trust me, they're super useful for representing and manipulating data.
Okay, matrices. I vaguely remember them from math class, but I'm not quite sure how they fit into data science.
Think of a matrix as a way to organize and transform data. You can represent things like customer purchase history, where each row is a customer and each column is a product.
Hmm.
The numbers in the matrix could be how much they bought, their ratings, or even just a yes or no for whether they bought it at all.
So like a super-powered spreadsheet.
That's a good way to put it. And one of the best things about matrices is that we can do math on them, like adding and multiplying, to actually manipulate the data in useful ways.
Okay, now you've got me curious. What kind of manipulations are we talking about?
Well, matrix multiplication that can be used for linear transformations might sound fancy, but it's super important for things like, image processing and recommendation systems.
Wait, hold on. How does multiplying matrices help with recommending products? That seems like a stretch.
Imagine that matrix representing customers and what they buy, like we talked about. We can break that matrix down using something called matrix factorization.
Okay, and what does that do?
It pulls out these smaller, easier to understand parts that reveal hidden relationships between customers and products.
So like it finds groups of customers who like similar things, or products that are usually bought together.
Exactly. It's like finding the underlying structure in the data. One technique is called singular value decomposition, or SVD.
SVD, that rings a bell. So it's like a pattern detector for data, right?
Exactly. And once we have those patterns, we can use them to guess what a customer might be interested in.
So if the SVD puts a customer in a group with others who bought a certain set of products, you recommend those same products to them.
Exactly. It's the math behind those customers who bought this also bought recommendations you see online.
Wow, that's so clever. So by getting the structure of the data, we make smarter recommendations. It's not just random guessing anymore.
Right on. And this is just the tip of the iceberg with what matrices can do in data science. They're used in everything from image recognition to natural language processing. But let's switch gears for a sec and talk about loss functions.
Okay, loss functions. Those sound kind of scary. What are they all about?
They're like the judges of our models. They tell us how well our models are doing by measuring the difference between what the model predicts and the actual data.
So like a scoring system for our model.
Mhm.
The lower the loss, the better the model is doing. But I bet there are different types of loss functions for different situations, right?
Absolutely. Depends on the specific problem, the kind of data you're dealing with. For example, if you have outliers in your data, those extreme values that are way off from everything else.
Like if one person spent a crazy amount of money and it skews the average.
Exactly. You'd want a robust loss function, one that's not too sensitive to those outliers. It's about making sure the judge is fair and considers the context.
Okay, I see how that's important. So how do we actually use these loss functions to make our models better?
They're the heart of model training. We use them to guide the learning process, kind of like adjusting knobs and dials on a machine to get the best output. One way to do this is called gradient descent, where you try to find the direction that decreases the loss the fastest and tweak the model accordingly.
So it's like finding the steepest path down a mountain.
Exactly. There are a bunch of different versions of gradient descent, but the main idea is to keep refining the model until the loss is as small as possible. But traditional machine learning often assumes things are, deterministic. Every input has one predictable output. Real life is messy, especially in e-commerce.
Right. People are unpredictable. So how do we account for that in our models?
Probabilistic modeling. Instead of trying to predict a single value, we estimate a whole range of possibilities.
So instead of saying a customer will spend $100, you say they're likely to spend between, say, $80 and $120.
Exactly. We're embracing the uncertainty instead of ignoring it.
That feels much more realistic.
Mhm.
So how do we build these probabilistic models?
It all starts with this idea of likelihood, how well our model explains the actual data we've seen. It's like asking, given our model, how likely is it that we would see the exact data we collected?
So high likelihood means the model is doing a good job of capturing the real world.
Right. Exactly. But what if we want to go even deeper? Not just checking if the model fits the data, but figuring out the probabilities of the model's own parameters.
That's a whole other level. We're looking inside the model now.
Exactly. That's where Bayes' theorem comes in. It's this powerful framework for updating our beliefs about the model based on the data.
Bayes' theorem. I've heard of it, but never really understood it.
Imagine you have a theory about customers. Let's say people who read reviews are more likely to buy. Bayes' theorem shows how to update that belief based on the data you collect.
Oh, so you start with an initial belief, gather evidence, and then adjust your belief based on what you find.
You got it. That's Bayesian modeling in a nutshell. It lets us combine what we already know with new data and even quantify how certain we are about the results.
Makes sense. But using Bayes' theorem on tricky problems sounds like a math nightmare.
It can be. There are two main ways to tackle it. One is to find a neat, closed-form solution, but that often means making some simplifying assumptions.
And those assumptions might not always hold up in the real world.
Exactly. So the other approach is computational sampling, specifically a technique called Markov chain Monte Carlo, or MCMC.
MCMC, yeah, it's like
Hey.
randomly exploring different possibilities for the model's parameters guided by the data.
Exactly. We're simulating lots of scenarios to get a good approximation of the answer, even if we can't solve it directly.
So we're embracing the messiness
Mm.
by trying out lots of possibilities.
Right. And thankfully, we have these tools called probabilistic programming languages, or PPLs, that make it easier to build these complex Bayesian models. They do a lot of the heavy lifting for us.
That's awesome. More brain power for the important stuff.
Exactly. Now let's dive into another key area, time series data.
Oh, that's data collected over time, right? Like website traffic or sales figure.
Precisely. It's everywhere in e-commerce. But
Okay.
when you're analyzing time series data, you have to be careful about something called autocorrelation.
Autocorrelation, what's that?
Yeah.
It means that what happens today is influenced by what happened yesterday, or even further back. Like, today's stock price is likely affected by yesterday's price and the price a few days ago.
Oh, so the past is connected to the present. That makes sense intuitively. But why is it so important for data analysis?
If you ignore autocorrelation, you can end up with models that don't really reflect reality. Imagine you're trying to predict sales, but you don't account for the fact that sales are always higher on weekends. Your model will be way off.
Ah, I see. The weekly ups and downs would mess things up. So how do we deal with this autocorrelation?
We have a tool called the autocorrelation function, or ACF, which helps us see how strongly the data is related to itself at different points in time.
So if the ACF shows strong connections, we know we need to account for those past influences.
Exactly. And that's where ARIMA models come in. They're designed to handle time series data with autocorrelation.
ARIMA, that stands for something, right?
Autoregressive integrated moving average. It's a whole family of models that combine three parts: autoregression, integration, and moving average.
Okay, let's break it down. What's autoregression?
Autoregression, or AR, is basically using past values of the data to predict future ones. It's like saying, if sales were high yesterday, they're likely to be high today too.
And integration.
Integration, or I, deals with making the time series stationary. That means its statistical properties, like the average and variability, stay pretty consistent over time.
So it's like smoothing out the data to make it easier to work with.
Exactly. And finally, you've got the moving average, or MA, component. That's about learning from our past prediction mistakes to improve future ones.
So it's like taking feedback from our errors and adjusting our predictions.
Exactly. So an ARTA model combines all three of these parts to get a really powerful tool for analyzing time series data. But choosing the right ARIMA model, that can get a bit tricky.
I can imagine. There's so many options.
There are techniques for figuring out the best settings, and even tools like auto.arima that try to automate the whole process for you.
So it's like having a smart assistant to help you pick the right model.
Exactly. But with all the fancy machine learning stuff out there, are ARIMA models still relevant these days?
That's a good question. Have they been completely replaced?
Not at all. While machine learning is definitely powerful, ARIMA models are still super useful because they're easy to understand, interpret, and they often perform surprisingly well.
Wow, so sometimes the classic approaches still hold their own.
They do. There was even this big forecasting competition called M5, where tons of complex machine learning models actually lost to a simple ARIMA-based approach.
Okay, that says a lot. Simple can be surprisingly effective.
Exactly. Now, let's switch gears again and talk about hypothesis testing.
Hypothesis testing. That's about figuring out if a difference we see in the data is real or just random chance, right?
Like, let's say you're comparing the average order value from two different marketing campaigns. You want to know if one is actually better than the other, or if the difference is just random noise.
So we're trying to separate the signal from the noise.
Exactly. We start with something called the null hypothesis. That's like our default assumption that there's no real difference between the campaigns. Then we have the alternative hypothesis, which says there is a difference.
And then we look at the data to see if we have enough evidence to reject that null hypothesis and say the difference is real.
You got it. One of the key tools here is the p-value. It tells us how likely it is that we'd see the data we got if there was actually no difference between the campaigns.
So a small p-value means it's unlikely that the difference is just random.
Exactly. It gives us more confidence to say that one campaign is truly better.
Okay, that makes sense. And are there different ways to calculate this p-value?
Yes. The book talks about different statistical tests like the z-test and t-test. Which one you use depends on your data and what assumptions you can make. But the book also warns about relying too much on p-values alone.
I've heard that. What else should we be looking at?
Effect size. It's about how big the difference actually is. Sometimes a statistically significant difference might be so tiny that it doesn't really matter in practice.
Like knowing that a certain color product sells a tiny bit better, but not enough to change our whole strategy.
Exactly. Sometimes a small difference isn't worth the effort. The book also talks about other approaches to hypothesis testing, like permutation tests, which are good when you have small samples or your data isn't nicely bell-shaped.
So there are different tools for different jobs.
Right. Now, once we've found a real difference, how do we actually measure how certain we are about our estimate?
Good question. Because our estimate is based on a sample, not the whole population.
That's where confidence intervals come in. They give us a range of plausible values for the real value we're trying to figure out. Instead of just saying the average order value for a campaign is $50, we might say it's between $45 and $55 with 95% confidence.
So it's like saying we're pretty sure the real value falls somewhere in this range.
Exactly. It acknowledges that our estimate isn't perfect, but it gives us a reasonable idea of where the true value might lie. But remember, a 95% confidence interval doesn't mean there's a 95% chance the real value is in that range.
Oh, that's tricky. So what does it actually mean then?
It means that if we ran the same experiment a bunch of times, 95% of the confidence intervals we calculate would contain the true value.
Okay, it's about the long-term performance of the method, not a single interval.
Exactly. The book shows how to calculate these confidence intervals for different situations. And related to this is the idea of power calculations, which help us figure out how much data we need to collect in the first place.
Power calculations. Sounds intense.
They help us avoid missing a real difference if it exists.
Oh, so it's about making sure our experiment has enough oomph to find something meaningful.
Exactly. Like if you're doing A/B testing on a website, a power calculation can tell you how many visitors you need to get reliable results.
That's super helpful. It's like planning ahead to make sure our experiment isn't a waste of time.
Exactly. Now let's switch gears one last time and talk about model complexity. It's another key thing to consider in data science.
Model complexity. I'm guessing that's about how complicated our models are.
You got it. The more complex a model is, the better it can fit the data. But there's a trade-off.
Oh, what's the catch?
Imagine you're modeling the relationship between website traffic and sales. You could use a simple linear model, assuming a straight line, or you could use a neural network with tons of parameters that can capture every little detail.
So more complex means more accurate.
Not always. Complex models are prone to overfitting. That's where the model basically memorizes the data it's been trained on.
So it gets really good at predicting the past, but not so good at predicting the future.
Exactly. It's like a student who just crams for a test but doesn't really understand the material.
I've been that student. Not the best strategy.
Right. Overfitting leads to bad predictions in the real world. On the other hand, if the model is too simple, it might miss important patterns. That's called underfitting.
So we need to find the sweet spot. Not too simple, not too complex.
Precisely. And that brings us to the bias variance trade-off.
Bias variance. Sounds like a mouthful.
Think of it like this. Bias is how far off our model's predictions are on average, while variance is how much those predictions jump around. Simpler models tend to have high bias but low variance, while more complex models have low bias but high variance.
So simpler models are consistent but maybe inaccurate, while complex models are accurate on average, but their predictions are less consistent.
Exactly. The trick is to find the right balance that minimizes both bias and variance.
Okay, so it's all about finding that sweet spot where the model is accurate and reliable.
Exactly. And this idea of breaking down complexity into simpler parts applies to more than just models. It also applies to functions. That's where function decomposition comes in.
Function decomposition, okay. Sounds like we're going deeper into the math now.
But it's a really intuitive idea. It's about taking a complicated function and breaking it down into smaller, simpler functions called basis functions.
Is there a real-world example of this?
Imagine a recipe. You can break down a complex dish into its basic ingredients, right? It's the same idea with functions.
Oh, okay. So each ingredient is like a basis function.
Exactly. And one classic example is the Fourier series, which lets us represent periodic functions, things that repeat over time as a sum of sine and cosine waves.
Oh, I've seen those visualizations where a square wave gets built up from smooth sine waves. Pretty cool how simple shapes can combine into something complex.
Exactly. The book even gives the formula for a Fourier series. It shows how to calculate the exact ingredients, so to speak. But what about functions that don't repeat?
Yeah, not everything in e-commerce follows a neat repeating pattern.
True. That's where Fourier transforms come in. They take the idea of the Fourier series and generalize it to any function, periodic or not. It's like looking at a signal from a different angle. Instead of seeing how it changes over time, we see what frequencies make it up.
So we're analyzing the building blocks of the signal instead of just the overall shape.
Exactly. And the book shows us how to switch back and forth between these two perspectives.
That's super cool. It's like having two different lenses to look at the same problem. But in e-commerce, we often deal with data that's not a continuous signal. It's more like a series of snapshots taken at specific times.
Absolutely. Think about things like daily website visits or individual customer purchases. Those are discrete data points.
So how do we apply these Fourier ideas to that kind of data?
We use something called the discrete Fourier transform, or DFT. It's like the digital version of the Fourier transform, specifically made for analyzing data that comes in chunks.
So we can use the DFT to find hidden patterns in our e-commerce data, right? Like those weekly or monthly cycles in sales or traffic.
Exactly. The DFT can break down the data into a bunch of sine and cosine waves, revealing those dominant frequencies hiding in the data.
That's awesome. So we can use these tools to uncover the rhythm of our business, so to speak.
You got it. Now, let's move on to another fascinating area of data science: network analysis.
Network analysis, I'm intrigued. What's that all about?
It's all about understanding relationships and connections in data, and graphs are the key.
Graphs, like the ones with nodes and edges.
Exactly. We use graphs to represent all sorts of connections. For example, you can have a graph where each node is a customer, and each edge shows whether two customers have bought the same product.
So we can visualize the whole web of connections between customers.
Exactly. And by analyzing this web, we can learn a lot about the structure of our customer base.
What kind of things can we learn?
Well, for example, we can identify influential customers who have connections to many other customers. These are like the hubs of the network.
Oh, so those would be like the trendsetters or early adopters who influence others. Interesting.
Exactly. Network analysis is a powerful tool for understanding complex systems, and it has tons of applications in e-commerce.
So we can use it for things like targeted marketing or even fraud detection.
Absolutely. By understanding the connections in our data, we can make better decisions about how to run our business. But remember, networks are constantly changing.
Oh, right. Relationships evolve over time. So how do we handle that?
That brings us to dynamical systems, which are systems that change over time.
So anything that evolves over time, like the stock market or customer behavior, can be considered a dynamical system.
Precisely. The book talks about two main types: continuous time systems, where time flows smoothly, and discrete time systems, where time jumps in steps.
Okay, so it's about how we model the flow of time. But then the book focuses on a special kind of dynamical system called a Markov process. What's special about those?
Markov processes are systems where the future only depends on the present, not the past. It's like saying that tomorrow's weather only depends on today's weather, not on what the weather was like last week.
So it's a system with a very short memory.
In a way, yes. And this property makes them easier to work with mathematically. They're defined by a transition matrix, which basically tells you the probabilities of moving from one state to another.
So we can use these transition matrices to predict how the system might change over time.
Exactly. And they have applications in lots of different fields, from predicting the spread of diseases to modeling customer behavior.
Wow, it's amazing how these mathematical concepts can be applied to such diverse problems.
It is. Now let's wrap things up with one last powerful technique: kernel methods.
Kernel methods. Those sound a bit intimidating. What are they all about?
They're a clever way to handle nonlinear relationships in data. Imagine you have data points that are all clumped together in a complex nonlinear way. Kernel methods can lift that data into a higher dimensional space where it might be easier to separate.
Okay, that sounds pretty abstract. Can you give me a real-world example?
Imagine trying to separate different colored marbles that are all mixed up in a bowl. It might be impossible to draw a straight line to separate them, but if you shake the bowl and let the marbles spread out in 3 dimensions, it might be easier to separate them by color.
Oh, I get it. It's like giving the data more room to breathe.
Exactly. And kernel methods let us do this without actually having to visualize the higher dimensional space. It's like a shortcut that lets us perform calculations in this higher dimension without actually having to go there.
That's pretty cool. But how do we know this shortcut actually works?
There is a theorem called Mercer's theorem that guarantees that for certain types of kernel functions, there exists a corresponding high-dimensional space where the data can be linearly separated.
Okay, so it's not just a trick. There's solid math behind it.
Exactly. And one commonly used kernel function is the radial basis function, or RBF kernel, which measures the similarity between data points based on their distance from each other.
So points that are close together in the original space will also be close together in this higher dimensional space.
You got it. And this property makes kernel methods really powerful for capturing complex relationships in data. They're used in lots of different machine learning algorithms, including support vector machines, which are great at classifying data.
So kernel methods can help us build better models by essentially giving the data a makeover.
Exactly. They're like a secret weapon for handling those tricky, non-linear relationships that often pop up in the real world.
Wow, this has been a whirlwind tour of some pretty mind-bending concepts. From probability and matrices to Fourier transforms and kernel methods, it's amazing how diverse and powerful the tools of data science are.
And we've only just scratched the surface. But hopefully this is giving you a good overview of some of the key ideas and how they can be applied to solve real-world problems.
Definitely. I'm feeling much more confident about tackling complex data sets now. But before we wrap up, I'm curious about one more thing. The book mentions information theory. What's that all about?
Great question. Information theory is all about quantifying information and uncertainty. It might seem a bit abstract, but it has surprisingly deep connections to data science. We'll dive into that next. Information theory. It's all about understanding, well, information and uncertainty. And it's got some pretty deep connections to data science.
Information theory. I always thought that was more about like sending messages and stuff, not really data science.
You're right. It started with figuring out how to send messages efficiently, even with noise on the line. But those same ideas are super useful in data science too.
Okay, I'm curious. How so?
It all comes down to quantifying information, like how much information is actually contained in a piece of data. And a key concept here is entropy.
Entropy. I remember that from physics. It's like a measure of disorder, right?
Exactly. And in information theory, entropy is all about measuring the uncertainty or randomness in a variable. Like imagine you're predicting customer churn.
Churn, whether a customer is going to leave or not. Right.
If your model says there's a 50-50 chance for every customer, that's high entropy, lots of uncertainty.
Well, we don't know which way it's going to go.
Right. But if your model gives you really confident predictions, like 90% likely to stay or churn, that's low entropy, less uncertainty.
So the more predictable something is, the lower its entropy.
Mm-hmm.
Makes sense. But you said this connects back to communication. I don't see the link yet.
Think about sending a message if it's something super predictable like, the sun will rise tomorrow. It doesn't take many bits to represent it.
You could basically sum it up in a few words.
Exactly. But a surprising message, something unpredictable, carries more information, so you need more bits to encode it. High entropy data is like that it's packed with potential information.
Oh, okay, I see. So entropy helps us measure how much juice is in the data, how much we can learn from it.
Precisely. And one practical use for this is in feature selection. Imagine you're building a model and you've got hundreds of variables.
Tons of data.
Right. But some of those variables might be really predictable and not add much new information.
They're just kind of repeating what other variables are already telling us.
Exactly. Entropy can help you spot those low information features and maybe even get rid of them, which can simplify your model and make it more efficient.
So it's a way to streamline our analysis, focus on what really matters. I like that. Are there other information theory concepts that are useful in data science?
Absolutely. Mutual information, for instance. It measures how much information two variables share. So if knowing a customer's age tells you a lot about their buying habits, those two variables have high mutual information.
Oh, that makes sense. Highly correlated variables are basically sharing information.
Exactly. And this can be super helpful when you're building a model. If two features have very high mutual information, you might only need to keep one of them.
To avoid redundancy, right?
Exactly. Information theory gives us tools to analyze these relationships.
This is really cool. It's making me think about information in a whole new way.
Right. It's not just about the data itself, it's about the patterns and relationships hidden within the data.
The underlying structure, the connections.
Precisely. Oh, and there's one more key concept I should mention, the Kullback-Leibler divergence, or KL divergence for short. It measures the difference between two probability distributions.
Okay, so now we're comparing whole distributions, not just individual variables.
Exactly. Think about it like this. Let's say you're trying to model customer spending habits.
Okay, I'm following.
There's a true distribution out there, the real-world patterns of how much people spend, but it might be really complex, so you come up with the simpler model to try and approximate it.
So it's like a simplified version of reality.
Right. And KL divergence tells you how much information you lose by using that simpler model.
So a low KL divergence means our approximation is pretty good.
Exactly. It's a way to see how well one distribution matches another. And this comes up a lot in model selection.
Oh, right, because you're always trying to find the model that best fits the data.
Exactly. You might try out different models and see which one has the lowest KL divergence to the true distribution.
I'm seeing how information theory is a lot more practical than it sounds at first.
Absolutely. It gives us this whole new set of tools for working with probability and understanding the information content of data.
I'm ready to add these to my data science toolkit. But the book also mentions non-parametric Bayesian methods. What are those all about?
Ah, good catch. They're a really cool set of techniques. Remember how we talked about parametric methods?
Yeah, where you assume a specific form for the model, like a linear relationship or a normal distribution.
Exactly, you're just estimating the parameters. But non-parametric methods are different. They're more flexible. They don't make such strong assumptions about the model's form.
So they let the data speak for itself more, adapt to the patterns we see, rather than forcing the data into a specific mold.
Exactly. Like, imagine you're trying to model customer buying behavior, but the relationship between all the different factors is super complex.
Way more than just a straight line.
Right. Non-parametric methods can handle that complexity without you having to specify the exact form of the relationship.
That sounds pretty powerful. But how do they actually work?
One famous example is Gaussian process regression, or GPR. Instead of assuming a fixed function, GPR defines a whole probability distribution over all the possible functions that could fit the data.
Wow, a distribution of functions. That's mind-blowing.
It is. It's like saying, we don't know the exact relationship, but here's our best guess, and here's how uncertain we are about it.
So it's not just giving us one answer, but a whole range of possibilities.
Exactly. And GPR uses those kernel functions we talked about earlier to define the relationships between data points. This allows it to learn complex patterns, make predictions about new data, and even give you confidence intervals that reflect the level of uncertainty.
So it's like, here's our best guess, and here's how much you should trust it.
Precisely. That's why GPR is great for situations where understanding uncertainty is crucial, like finance or medicine.
Makes sense. Are there other types of non-parametric Bayesian methods?
Definitely. Another important one is Dirichlet processes, or DPs. They're used to model probability distributions themselves.
Wait, so instead of assuming a normal distribution or a binomial distribution, we're modeling the uncertainty about the distribution itself.
You got it. It's like a distribution of distributions. It sounds crazy, but it's all about being more flexible and letting the data guide us.
Okay, I'm trying to wrap my head around that. So how are these Dirichlet processes used in practice?
One common application is in clustering. Like, imagine you're trying to group customers based on their buying habits. You might not know how many groups there are beforehand.
Right, you don't want to force the data into a predetermined number of categories.
Exactly. Dirichlet processes can figure out the most likely number of clusters based on the data itself.
So they can find those natural groupings without us having to tell them how many groups to look for.
Exactly. That can be super helpful for things like targeted marketing. You want to send the right message to the right group of customers.
This is really cool stuff. It seems like non-parametric Bayesian methods are all about letting the data guide the analysis rather than imposing our own assumptions.
You got it. They're all about flexibility, adaptability, and embracing uncertainty.
Okay, my brain is officially full. That was a whirlwind tour of some pretty heavy concepts, from information theory to Bayesian modeling and beyond. But it's amazing to see how these seemingly abstract mathematical ideas can have such practical uses in data science.
Absolutely. And it all comes down to extracting meaningful insights from data so we can make better decisions.
Whether we're trying to understand customer behavior, predict market trends, or optimize our business, These tools are changing the game.
They are. And the best part is we're just getting started. The field of data science is constantly evolving, and there's always something new to learn and explore.
I'm definitely feeling inspired to dive deeper into these topics and see how I can apply them in my work.
That's the spirit. And remember, the most important thing is to use these tools responsibly and ethically, always considering the real-world consequences of our analyses.
Well said.
Yeah.
But before we wrap up entirely, you mentioned something about random matrix theory earlier. What's that all about? It sounds intriguing. Random matrix theory. That sounds intense.
It is a bit specialized, but it's got some surprisingly wide applications. It's all about matrices where the entries are random variables.
So instead of fixed numbers in the matrix, we have probabilities. I'm already lost. Can we bring this back to e-commerce?
For sure. Let's imagine you're looking at customer purchases for a huge online store. You've got thousands of customers and thousands of products. You can represent that data as a matrix. Each row is a customer. Each column is a product.
Okay, like a giant spreadsheet. How does randomness fit in?
Well, customers are unpredictable, right? You can't know for sure if they'll buy something. So instead of just ones and zeros for purchases, you can think of each entry as a probability, the chance of a purchase.
So we're factoring in the uncertainty. Each cell is like, maybe they'll buy it, maybe not.
Exactly. We're embracing the randomness. But here's where random matrix theory gets really cool. It turns out that even though the individual entries are random, if you look at a big enough matrix, it starts to show some predictable patterns.
Wait, hold on. How can random stuff become predictable?
It's one of those amazing things about math. As the matrix gets bigger, some of its properties become more and more certain, like the distribution of its eigenvalues.
Eigenvalues, those special values we talked about with SVD.
Exactly. And those eigenvalues can reveal hidden structures in the data, like clusters of customers who buy similar things, or groups of products that are often bought together.
So even though individual customers are random, when we zoom out and look at the whole system,
We see patterns emerge. It's like finding order within the chaos.
that's amazing. So random matrix theory helps us see the bigger picture.
Precisely. And those insights are super valuable for e-commerce. You can personalize recommendations better, manage inventory more efficiently.
It's like using randomness to our advantage.
Exactly. It shows how different areas of math, linear algebra, probability, statistics all come together in data science.
I'm seeing that more and more it's all connected. Well, I'm feeling a lot more equipped to tackle those giant data sets now, thanks to all the tools we've explored today.
That's what this deep dive is all about. We've covered a ton: probability, stats, linear algebra, information theory, even some of those fancy modeling techniques.
It's been quite a journey. I feel like we've opened up this whole new world of possibilities.
And remember, this is just the beginning. Data science is always changing, so keep exploring and keep learning.
I definitely will. This deep dive has sparked my curiosity for sure.
That's great to hear. And always remember to use these tools responsibly and ethically.
Absolutely. To our listener, thanks for joining us on this deep dive into the fascinating world of data science math. I hope you've gained some valuable knowledge and a new appreciation for the power of math to help us understand the data all around us.
Until next time, keep exploring, keep learning, and keep diving deep into those data sets.